Hi everyone, and welcome back to Fundamentals of Engineering with Farhad, Mechanics of Materials, Strain Energy. In this example, we want to talk about the strain energy stored in variable cross sections, like calculation of U in a tapered cone, which has a variable cross section area. And also the other situation, which is again a variable cross section, is a stepped cone. So both of them handling concentrated load of P at their center, and they are identical to each other. And they are similar to each other. In this video, we review the calculation of strain energy in tapered cone, and in the next we talk about strain energy calculated in a stepped cone and make a comparison between them. So let's jump to the tapered cone for now. Again, we need to extend our mm, uh, tapered cone to have like a entire cone to get the relation between the length and diameter of our cross sections. So in our tapered cone, if we just jump to the relation of the length, for example, L sub A to L sub B, length from the arbitrary origin O to the minimum cross section or first cross section is LA, and from the origin to the last one is LB, and LA over LB is equal to the ratio of their diameter dA over dB. If we define a middle cross section like dx with the distance located from the origin by the distance of x, then this element is traveling from the beginning of the sample to the end, like traveling alongside the cone and create the whole shape. So dx is our differential form of our cross section, dx over dA. This time we have the same relation, but this time based on x and LA. So dx over dA is equal to x over LA. Then we get the parametric form of our differential equation for dx, which is x dA over LA. And definitely ax is nothing but pi dx squared over 4. So as soon as we have like our area in terms of cross-sectional parametric cross-section, then we can just jump to the formula for strain energy and just replace the parametric format of our area ax, which is pi dA squared times x squared over 4 LA, length of the first one squared. The formula for strain energy stored in variable cross section is equal to U. Capital U is equal to integration. Our limit of integration is L, like LA is equal to L, and LB is equal to 2i's of that based off problem statement. And then sigma squared over 2 modulus of elasticity times dV, a volume element. So we simply know sigma stress is force over the area, and our cross-sectional area is a function of x. That's why we had to calculate ax at the beginning. As soon as we have that, and by simply replace sigma like p over a in the stress equation and jot down the strain energy again, it just gives us this equation: integration of L to 2L pi squared over 2e times ax squared, then times the element of volume dv. Now this time let's expand the dv, and dv, the differential form of a volume is area times x, so that's ax times dx. And if you just simply replace dv by ax dx, and one of uh, this ax in the numerator is cancelled out by one of those two ax to this ax squared. One of them is cancelled out with the from numerator with the denominator, and then if you simplify the equation, it just gives you u equal to integration from L to 2L pi squared over 2eax dx. And we already calculate the parametric format of ax, which gives us this equation. Replace this in the main equation, then rewrite or jot down again the equation of u. It just gives you this equation, the bottom one for u. And as soon as you have that, get the constant out of the integration. So all this part is a constant, and they just came out of the integration. So what I mean is, like, all this part is just a constant comes out of the integration, and then just the integration of a x over dx over x squared dx from L to 2L. And if you do the math for this integration, it just gives you a negative 1 over x from L to 2L. If you do the math, it just gives you 1 over 2L. Replace it back to the main equation and just consider pi times dA squared over 4 is a minimum. So it just gives you a strain energy stored in a tapered cone is equal to pi squared times the length times over 4 times modulus of elasticity and area minimum, which area minimum stands for the first cross section, which is here. Thank you. So this is the strain energy stored in a variable cross section, but this time for tapered cone condition, U is equal to pi squared L over 4E times area minimum, which is again a minimum, is the first area, which stands for a min, and this is like a max. Thank you. Next time we'll solve the same problem, but this time with a similar but a stepped cone, and make a comparison between the result of the two problems. Thank you. See you on next video.